Simple and effective masked diffusion language models. Authors: Subham Zeka Sahu, Marianne Ariola, Yair Schiff, Aaron Gokaslan, Edgar Marokin, Justin Tichiu, Alexander Roche, Volodymyr Kuleshov. All authors are affiliated with Cornell Tech, New York City, USA. Contact emails are provided for each author. Abstract. While diffusion models excel at generating high-quality images, prior work reports a significant performance gap between diffusion and autoregressive methods in language modeling. In this work, we show that simple masked discrete diffusion is more effective than previously thought. We apply an effective training method that improves the performance of masked diffusion models and derive a simplified objective, called Rao-Blackwellized objective, that results in additional improvements. Our objective has a simple form. It is a mixture of classical masked language modeling losses and can be used to train encoder-only language models that allow for efficient sampling, including models that can generate arbitrary lengths of text semi-autoregressively, like a traditional language model. On language modeling benchmarks, a range of masked diffusion models trained with modern engineering practices achieves a new state-of-the-art among diffusion models and approaches the performance of autoregressive models. Introduction. Diffusion models excel at producing realistic, high-quality images and have received significant attention as potential tools for generating discrete data, such as text, biological sequences, and graphs. Unlike autoregressive approaches, diffusion-based methods are not constrained to generate data sequentially. Therefore, they have the potential to improve long-term planning, controllable generation, and sampling speed. However, discrete diffusion methods exhibit a performance gap relative to autoregressive models, especially in language modeling. The standard measure of language modeling performance is log likelihood. When controlling for parameter count, prior work reports a sizable log likelihood gap between autoregressive and diffusion models. In this work, we show that simple masked diffusion language modeling, combined with effective training methods, is more effective than previously thought. We develop a well-engineered masked diffusion language modeling implementation that significantly improves discrete diffusion log likelihood. We further improve likelihood using a simple substitution-based parameterization of the reverse diffusion process. This enables us to derive a Rao-Blackwellized continuous time variational lower bound, also known as ELBO, with improved tightness. Interestingly, our objective has a simple form. It is a weighted average of masked language modeling losses and can be used to give BERT style, encoder-only models principal generation capability. We complement this framework with efficient samplers, including ones that can generate semi-autoregressively like a typical language model. Our masked diffusion models achieve a new state-of-the-art among diffusion models on language modeling benchmarks and approach the perplexity of autoregressive models within 15 to 25%. Surprisingly, simple engineering choices significantly improve performance in both our models and simple baselines that were previously thought to perform poorly. Our framework also extends to non-language domains, including biological sequence modeling. We pre-train DNA sequence models and observe similar or higher downstream performance compared to classical BERT-style training, while also introducing generative capabilities that classical masked DNA language models lack. Contributions. We describe a simple mask diffusion language modeling framework with a well-engineered implementation that outperforms all existing diffusion models across language modeling benchmarks. These benchmarks include 1 billion words, open web text, and DNA sequence modeling. Our framework significantly improves the performance of existing baselines. Our mask diffusion language modeling framework implements a substitution-based parameterization of the reverse unmasking diffusion process. This allows us to derive a simple continuous time, Rao-Blackwellized objective that improves the tightness and variance of the ELBO, further increasing performance. We complement masked diffusion language modeling with fast samplers that support semi-autoregressive generation and outperform previous semi-autoregressive models. Figure description. The figure on the left shows our proposed masked diffusion language model, which is trained using a weighted average of mask cross-entropy losses. The top right part of the figure compares masked language models and our masked diffusion language model, showing that our objective corresponds to a principled variational lower bound and supports generation via ancestral sampling. The bottom right part of the figure displays the perplexity on the 1 billion words benchmark. Section Background. Diffusion models. Diffusion models are trained to iteratively undo a forward corruption process that takes clean data drawn from the data distribution and defines latent variables over time. These latent variables represent progressively noisy versions of the clean data. The standard forward process for continuous data involves adding noise in a controlled manner. The noisy version at time tt is given by the square root of yhat times the clean data plus the square root of 1 minus yhat times some noise. The noise follows a normal distribution, and yhat is a noise schedule that decreases over time. The parameterized reverse diffusion model is trained to maximize a variational lower bound on log likelihood, known as ELBO. Given a number of discretization steps, the negative ELBO is calculated using the callback-Leibler divergence. The negative ELBO consists of 3 parts: the reconstruction loss, the diffusion loss, and the prior loss. For brevity, we omit the specific time steps in the equations below. In general, the earlier time step is denoted by SS, and the later time step by TT. Subsection Discrete diffusion models. Applications of diffusion modeling to discrete data can be divided into 2 broad categories. The first category includes works that embed discrete structures in continuous space and then perform Gaussian diffusion on these continuous representations. The second category, which is more related to our method, includes works that define a diffusion process directly on discrete structures. The D3PM framework introduces a Markov forward process defined by the multiplication of matrices over discrete time steps. This process represents the discrete state form of the continuous diffusion process mentioned earlier. Extending this formalism to continuous time relies on continuous time Markov chain theory. This framework leads to generalizations of the score matching perspective on diffusion modeling to discrete data. Notably, the SED approach connects score-based approaches with ELBO maximization, enabling effective likelihood-based training of score-based models. Section Simple masked diffusion models. Previous work on discrete diffusion supports general forward processes. However, absorbing state diffusion, also known as masking diffusion, consistently achieves the best performance. In this work, instead of supporting general noise processes, we focus on masking and derive tight, Rao-Blackwellized objectives that outperform general approaches and do not require complex theory. In this section, we first define the diffusion process for a categorical random variable. Later, we extend this process to sequences containing multiple such categorical variables. We denote our overall approach as masked diffusion language models, MDLM. Notation, INT. We denote scalar discrete random variables with a certain number of categories as one-hot column vectors. The set of all such vectors is defined as those vectors where only one element is 1 and the rest are 0. The categorical distribution over these categories is denoted as cat with probabilities given by prior. We assume that the last category corresponds to a special mask token and let me the one-hot vector for this mask. Additionally, let 1 be a vector of 1s, and let the dot product and Hadamard product between 2 vectors be denoted as a dot B and a Hadamard B, respectively. Subsection Interpolating discrete diffusion. We focus on forward processes that interpolate between clean data and a target distribution, forming a direct extension of Gaussian diffusion. These processes define a sequence of increasingly noisy latent variables, where the time step runs from 0, which is least noisy, to 1, which is most noisy. The marginal of the noisy data conditioned on the clean data at a given time is defined by a categorical distribution. This implies that during each diffusion step, a fraction of the probability mass is transferred to the prior distribution. The reverse posterior is given by a specific formula that simplifies the general diffusion processes. This yields a simplified variational lower bound objective and allows for straightforward continuous time extensions. Subsection: Mask diffusion. Next, we focus on masking processes and derive a simple Rao-Blackwellized objective for this choice of forward process. This objective incurs lower variance during training and improves tightness. Subsection: Forward masking process. In masked or absorbing state diffusion, we set the prior equal to the mask token. At each noise step, the input transitions to a mask state with some probability. If an input transitions to the mask state at any time, it will remain in this state for all subsequent times. At the final time step, all inputs are masked with probability 1. The marginal of the forward process is given by a weighted combination of the input and the mask token. Using properties of the masking process, the posterior simplifies as follows. If the noisy variable is not the mask, the posterior is equal to the noisy variable. If the noisy variable is the mask, the posterior is a weighted combination of the mask and the input. Subsection: Reverse unmasking process. The reverse process undoes the noise process defined by the forward process. We consider both a finite number of steps as well as a continuous time model. We begin with the discrete time case, where the generative model is expressed as a product of transition probabilities. The optimal form for the reverse transition matches the true posterior. This follows from the definition of the diffusion objective, which is a sum of Kullback-Leibler divergence terms. However, the true posterior is conditioned on the clean data, which we do not know. Therefore, we introduce a model that approximates the clean data with a neural network. We can also omit explicit dependence on time, which simplifies sampling and speeds up inference. Subsection: Specific parameterization. The specific parameterization for the reverse transition that we use is as follows. If the noisy variable is not the mask, the reverse transition is equal to the noisy variable. If the noisy variable is the mask, the reverse transition is a weighted combination of the mask and the approximate clean data. We induce two key properties of the absorbing state diffusion process into our denoising model. First, an input token remains unchanged during reverse diffusion, and second, the clean input is never masked. We implemented these as substitutions to the output of our model, hence, we call our parameterization SUBs. Zero masking probabilities. First, by definition, the inner product of the input and the mask is 0. Therefore, we design the denoising network such that the approximate clean data for the mask token is 0. We achieve this by substituting the logit index corresponding to the mask token with negative infinity. Carryover unmasking. Second, if the noisy variable is unmasked, then we desire the approximate clean data to equal the noisy variable. We accomplish this by substituting the output of our network to simply copy unmasked inputs. In our supplementary material, we show that the zero masking probabilities property simplifies the negative ELBO to a simplified form, and the carryover unmasking further simplifies it. Each simplification leads to an improved likelihood. Subsection: Rao-Blackwellized likelihood bounds. Recall from the earlier discussion that the diffusion training objective consists of 3 parts: reconstruction loss, diffusion loss, and prior loss. For the simplified reverse process, the discrete time diffusion loss for a finite number of steps simplifies to a specific equation. This objective is simpler and more well-behaved than the expression one would obtain under the parameterization used by D3PM. The process of obtaining the simplified diffusion loss instead of the unsimplified one is a form of Rao-Blackwellization. Specifically, we analytically compute expectations to simplify the objective. Without these simplifications, a model must learn parameters to ensure certain conditions hold. Unlike regular Rao-Blackwellization, these simplifications are possible because of our modeling choices. Our approach also empirically helps reduce variance, so we refer to it as Rao-Blackwellization, somewhat abusing the usual terminology. Subsection: Continuous time likelihood bounds. Previous works have shown that increasing the number of steps yields a tighter approximation to the ELBO, which is the evidence lower bound. Following a similar argument, we form a continuous extension of the simplified diffusion loss by taking the number of steps to infinity. This yields a continuous time negative ELBO. The function involved in this process is invertible due to the monotonicity assumption discussed earlier. Therefore, we can perform a change of variables to express the diffusion loss equivalently. This new formulation demonstrates that the diffusion loss is invariant to the functional form of the noise schedule, which we verify empirically. Subsection: Masked diffusion language models. Next, we apply masked diffusion to language modeling over sequences of tokens. We assume that the forward noising process is applied independently across a sequence and that, conditioned on a sequence of noisy variables, the denoising process factorizes independently across tokens. Thus, we use a single model to compute the denoising function for each token from a masked sequence, optimizing a continuous time negative ELBO. Interestingly, our objective has a simple form. It is the weighted average of masked language modeling losses. This establishes a connection between generative diffusion models and encoder-only BERT models. Our objective enables the principled selection of a randomized masking rate and endows BERT-style models with principal generation capabilities. Subsection: Training considerations for masked diffusion. One of the key contributions of our work is a well-engineered implementation of masked diffusion models. Our experiments demonstrate that these improvements greatly boost performance, even for methods previously thought to perform poorly. First, we find that tokenization is critical to performance. Small vocabularies result in longer range dependencies that decrease the performance of both diffusion and autoregressive models. Additionally, by focusing on masked diffusion, we are able to provide a numerically stable implementation of the objective function. Previous formulations of discrete diffusion were constructed to accommodate a wide range of limiting distributions. In contrast, we evaluate the Kullback-Leibler divergence by examining only the masked token indices rather than comparing the full true and approximate posterior distributions. Furthermore, we modernize the architecture for the denoising network relative to previous work. Instead of using the T5 architecture, we use the diffusion transformer, which integrates time-step conditioning into a standard encoder-only transformer and uses rotary positional embeddings. In addition, we implement a low-discrepancy sampler that reduces the variance of the ELBO and draws correlated samples rather than performing independent sampling. Section: Inference and sampling in masked diffusion language models. Subsection: Efficient ancestral sampling. To generate a sequence of length L, the reverse diffusion process starts with the sequence at the final time step, where each token is masked. Then, the subsequent latent variables are generated by discretizing the reverse diffusion process with a finite number of steps. Given the latent variables at time t, we construct the variables at the previous time step by sampling each token independently from the distribution given in the earlier discussed equation. In the reverse process, unmasked tokens remain unchanged. Therefore, if no new tokens become unmasked in the transition to the previous time step, the sequence remains the same. Additionally, if the denoising model is not conditioned on time, we can simply draw a new sample using the previously computed and cached value. This means we effectively skip over the time step, saving a function call to the denoising network. Note that another method does not support this catching because its denoising network models time-dependent rates, which requires conditioning on time. Subsection: semi-autoregressive mask diffusion language models. Our method also supports an effective semi-autoregressive decoding method that allows the model to generate sequences of arbitrary length. Let the initial output represent the sequence of L tokens generated using the reverse diffusion process described above. To generate additional tokens, we propose a generation algorithm where the latter part of the sequence is used as a prefix for an additional round of generation. Given the carry-over unmasking described earlier, these prefix tokens will simply be copied over at each decoding step. The remaining tokens are generated as before, with the initial tokens set to the previously generated sequence instead of being initialized as masked tokens. At the end of this process, we have produced a concatenated sequence of the original and newly generated tokens. This process can repeat indefinitely, with the prefix shifted for every new round of generation. Section: experiments. Subsection: masked diffusion language models. Experimental setup. We evaluate our algorithm as a generative model of language and as a representation model via fine-tuning on downstream tasks. For language modeling likelihood evaluation, we conduct experiments on two datasets, the 1 billion words dataset and OpenWebText. We use a specific tokenizer for 1 billion words and report perplexities on the test split. Models have a context size of 128. For OpenWebText, which does not have a predefined split, we reserve the last 100,000 documents as a held-out validation set and report perplexities on this set. We use the GPT-2 tokenizer for OpenWebText. Models have a context size of 1024. We utilize the transformer architecture, which augments the diffusion transformer with rotary embeddings. Our algorithm was trained for 1 million or 10 million steps on 1 billion words and 1 million steps on OpenWebText. The corresponding autoregressive baseline was trained for half the number of steps to ensure a similar number of tokens seen. Full hyperparameters are given in the appendix. For representation learning, we pre-train models on the C4 dataset, then fine-tune and evaluate models on the GLUE benchmark. Models have a context size of 128. We use the BERT-based uncased tokenizer for the representation learning experiments. We utilize the Mosaic BERT architecture, an extension of the original BERT architecture. We pre-train a bidirectional Mosaic BERT using a masked language modeling objective for 37 billion tokens of C4, as well as a causal variant on the same data. We further fine-tune the Mosaic BERT model using our algorithm for 327 million tokens, less than 1% of the pre-training data. We provide the full hyperparameters in the appendix. Table: test perplexities on 1 billion words. Autoregressive models. Transformer X-base has 460 million parameters and a perplexity of 23.5. Omninet T has 100 million parameters and a perplexity of 21.5. Diffusion models. BERT mouth has 110 million parameters and a perplexity less than or equal to 142.89. D3PM absorb has 70 million parameters and a perplexity less than or equal to 77.5. Diffusion LM has 80 million parameters and a perplexity less than or equal to 118.62. Diffusion BERT has 110 million parameters and a perplexity less than or equal to 63.78. SEDD with 33 billion tokens has 110 million parameters, and a perplexity less than or equal to 32.79. Autoregressive retrained. Transformer with 33 billion tokens has 110 million parameters, and a perplexity of 22.322. Transformer with 327 billion tokens has 110 million parameters, and a perplexity of 20.86. Diffusion hours. Our algorithm with 33 billion tokens has 110 million parameters, and a perplexity less than or equal to 27.04. Our algorithm with 327 billion tokens has 110 million parameters and a perplexity less than or equal to 23. Likelihood evaluation. On 1 billion words, our algorithm outperforms all previous diffusion methods. Compared to the SEDD baseline trained for 66 billion tokens, our algorithm, trained for the same amount, achieves a 17% improvement on the perplexity bound. Finally, our algorithm gets within 14% of an autoregressive baseline and continues to improve with more training. We see the same trend from models trained on open web text, a larger dataset. Our algorithm outperforms prior diffusion methods, closing the gap towards autoregressive models. Results on open web text with time-step conditioning show that models trained with and without time conditioning attain similar perplexities. Additionally, Figure 1 demonstrates the reduced variance we achieve from our objective compared to previous mask diffusion models, such as SEDD. Zero-shot likelihood evaluation. We also explore models' ability to generalize by taking models trained on open web text and evaluating how well they model unseen datasets. We compare the perplexities of our algorithm with a SED parameterization and an autoregressive transformer language model. Our zero-shot datasets include the validation splits of Pentree Bank Wikitext, 1 billion words, Lambda, AG News, and scientific papers, PubMed and ArXiv subsets. Full experimental details are available in the appendix. Our algorithm consistently outperforms the SED diffusion parameterization. In some cases, such as for Lambda and scientific papers, our algorithm attains better perplexity than autoregressive models. We hypothesize that these datasets are farther from open web text and that diffusion models may be more robust to out-of-domain evaluation due to the unmasking-based objective. Table: Zero-shot validation perplexities. Pentree Bank. Autoregressive model perplexity is 82.05. SEDD perplexity is 100.09. Our algorithm perplexity is 95.26. Wikitext. Autoregressive model perplexity is 25.75. SEDD perplexity is 34.28. Our algorithm perplexity is 32.83. 1 billion words. Autoregressive model perplexity is 51.25. SEDD perplexity is 68.2. Our algorithm perplexity is 67.01. Lambda, autoregressive model perplexity is 51.28. SED perplexity is 49.86. Our algorithm perplexity is 47.52. AG News. Autoregressive model perplexity is 52.09. SEDD perplexity is 62.09. Our algorithm perplexity is 61.15. PubMed. Autoregressive model perplexity is 49.01. SEDD perplexity is 44.53. Our algorithm perplexity is 41.89. ArXiv. Autoregressive model perplexity is 41.73. SED perplexity is 38.48. Our algorithm perplexity is 37.37. Downstream task evaluation. We find that BERT fine-tuned with our algorithm to be a generative model results in strong perplexities, while preserving performance on downstream tasks. On the C4 validation set, the autoregressive model attains a perplexity of 22. The pre-trained BERT attains a perplexity upper bound of 78, and BERT, fine-tuned with our algorithm, attains a perplexity upper bound of 35. In the GLUE evaluation, we find that BERT, fine-tuned with our algorithm, has no degradation in downstream performance compared to the BERT initialization. While the perplexity of our method is higher than the autoregressive baseline, the downstream task performance is significantly better. Table. GLUE evaluation results. MLLI match and mismatch. Autoregressive model scores 80.94 and 80.78. BERT scores 84.43 and 85.35. BERT, fine-tuned with our algorithm, scores 84.76 and 85. QQP. Autoregressive model scores 86.98 part 2. BERT scores 88.41. BERT, fine-tuned with our algorithm, scores 88.49. QNLI. Autoregressive model scores 86.16. BERT scores 90.46. BERT, fine-tuned with our algorithm, scores 90.3. SST2. Autoregressive model scores 90.14. BERT scores 92.22. BERT, fine-tuned with our algorithm, scores 92.2. COL. Autoregressive model scores 33.43. BERT scores 54.81. BERT, fine-tuned with our algorithm, scores 57.69. STSB. Autoregressive model scores 84.32 DN. BERT scores 88.41. BERT, fine-tuned with our algorithm, scores 87.48. MRPC. Autoregressive model scores 83.818. BERT scores 89.16. BEE. RT, fine-tuned with our algorithm, scores 90.53. RTE. Autoregressive model scores 47.29. BERT scores 61.37. BERT, fine-tuned with our algorithm, scores 62.09. Average scores. Autoregressive model scores 74.88. BERT scores 81.62. BERT, fine-tuned with our algorithm, scores 82.6. Semi-autoregressive modeling. To test the semi-autoregressive decoding algorithm, we compare to a diffusion model that was designed to generate blocks of text autoregressively. We generate 200 sequences of length 2048 tokens on a single GPU and evaluate generative perplexity under a pre-trained GP2 model. The other model sequences are generated using blocks of 25 tokens, and our sequences are generated using 512 tokens. In the comparison, we find that in addition to achieving better generative perplexity, our algorithm enables 25 to 30 times faster semi-autoregressive decoding relative to the other model. Table. Semi-autoregressive generative perplexity. Generative perplexity in seconds per sequence. The other model has a generative perplexity of 35.43 and takes 2,473.9 seconds per sequence. Our algorithm has a generative perplexity of 27.8 and takes 89.3 seconds per sequence. Subsection. Masked diffusion DNA models. We also explore the use of our generative formulation in conjunction with structured state space models. We build on the recently proposed Caduceus model, which uses the data-dependent SSM-Mamba block as a backbone. Experimental setup. We pre-train the encoder-only Caduceus model, which is a masked language model, on the HD38 human reference genome and perform fine-tuning using our diffusion parameterization. We use a context length of 1024 tokens and follow the previous experimental setup other than the learning rate, which was reduced. Full experimental details are available in the appendix. We assess both generative performance using perplexity and downstream performance on genomics benchmarks across language diffusion, paradigms, and autoregressive models. Generative performance. We fine-tune the Caduceus masked language model across diffusion parameterizations and compare perplexities against autoregressive models. We report perplexity values in the table below. Our algorithm outperforms all other diffusion language modeling schemes. Table. Test perplexities of generative fine-tuning on the HD38 reference genome. Autoregressive models. Mamba has 465,000 parameters and a perplexity of 3.067. Huyanadna has 433,000 parameters and a perplexity of 3.153. Diffusion models. Plaid has 507,000 parameters and a perplexity less than or equal to 3.24. SEDD has 467,000 parameters and a perplexity less than or equal to 3.216. Our algorithm has 467,000 parameters and a perplexity less than or equal to 3.199. Downstream task fine-tuning. We perform downstream evaluation with the genomics benchmarks, a recently proposed benchmark with 8 regulatory element classification tasks. As shown in the table below, our generative fine-tuning paradigm preserves or improves upon downstream performance from masked language model pre-training. Absorbing state diffusion methods outperform Plaid across tasks, except for the simplest task human versus worm, where all methods have roughly the same performance. For tasks where the input is a biased subsample of the full genome, we observe that the correlation between perplexity and downstream performance is weaker. Table genomic benchmarks. Mouse enhances EUN. AR Mamba scores 0.763. Caduceus MLM scores 0.81. Caduceus Plaid scores 0.745. Caduceus SEDD scores 0.784. Caduceus with our algorithm scores 0.795. Coding versus intergenomic. AR Mamba scores 0.897. Caduceus MLM scores 0.9130. Caduceus Plaid scores 0.908. Caduceus SEDD scores 0.93. Caduceus with our algorithm scores 0.930. Human versus national inequality. Worm. AR Mamba scores 0.967. Caduceus MLM scores 0.97. Caduceus Plaid scores 0.978. Caduceus SEDD scores 0.97. Caduceus with our algorithm scores 0.97. Human enhances cone. AR Mamba scores 0.734. Caduceus MLM scores 0.737. Caduceus Plaid scores 0.743. Caduceus SEDD scores 0.746. Caduceus with our algorithm scores 0.743. Human enhancer ensemble. AR Mamba scores 0.856. Caduceus MLM scores 0.907. Caduceus Plaid scores 0.885. Caduceus SEDD scores 0.905. Caduceus with our algorithm scores 0.899. Human regulatory AR Mamba scores 0.861. Caduceus MLM scores 0.874. Caduceus Plaid scores 0.86. Caduceus SEDD scores 0.828. Caduceus with our algorithm scores 0.868. Human OCR Ensemble AR Mamba scores 0.806. Caduceus MLM scores 0.821. Caduceus Plaid scores 0.82. Caduceus SED scores 0.816. Caduceus with our algorithm scores 0.823. Human non-data promoters AR Mamba scores 0.926. Caduceus MLM scores 0.935. Caduceus Plaid scores 0.935. Caduceus SEDD scores 0.935. Caduceus with our algorithm scores 0.94. Subsection Ablation Analysis. In the table for ablation analysis, we can see the effect of our streamlined mask diffusion implementation. The improvements described in the improved implementation section allow us to greatly reduce perplexity of previously discounted models such as D3PM. The bottom row of this table is mathematically equivalent to the D3PM formulation. While most works assume that D3PM achieves mediocre log likelihoods, we show that is incorrect. Our re-implementation almost matches state-of-the-art score-based methods. This introduces a new strong baseline that opens new research opportunities. Additionally, in the table, we ablate different components of our algorithm. We observe that the perplexity for our algorithm trained with a discrete time of 1000 marginally worsens by 0.1 compared to our algorithm trained in continuous time. Additionally, removing the carryover operation from the parameterization increases the perplexity by 1.5 points. However, further removing the zero masking operation does not lead to any meaningful change in perplexity. We provide further ablations for the continuous time formulation in the appendix, showing in the supplementary figure that for a pre-trained model, at inference, increasing the number of steps yields better likelihood. Table. Test perplexities for ablations on 1 billion words. For the discrete time models, we use a time of 1000. Standard deviation is measured over 5 seeds during evaluation. Our algorithm in continuous time has a perplexity of 27.04, with a standard deviation of 0.01. Without continuous time, the perplexity is 27.19, with a standard deviation of 0.07. Without carryover, the perplexity is 28.56, with a standard deviation of 0.115. Without zero masking, the perplexity is 28.51 with a standard deviation of 0.150. Section Discussion, Prior Work and Conclusion. Comparison to D3PM. Mask diffusion is a strict subset of D3PM. Setting a matrix in their framework yields our forward diffusion. We improve over D3PM in 3 ways. First, we adopt the SUBS parameterization for the reverse process. Second, this allows us to derive a simplified objective that analytically simplifies certain expectations to 0. Third, we adopt well-engineered training recipes that improve performance. Both the first and second improvements are possible because we focus on masking instead of developing a general discrete diffusion framework. Surprisingly, the third improvement has the largest contribution to performance. Comparison to continuous time Markov chains. Most implementations of diffusion work best in continuous time. However, extending D3PM in this way requires computing the limit of the product of an infinite number of matrices as the number of steps approaches infinity, which requires advanced continuous time Markov chain theory. Our work describes simple continuous time formulations for the most common noise processes, such as masking and uniform prior, thus helping make an important part of the literature more accessible. Our results remain compatible with continuous time Markov chains. We effectively use rate matrices. Comparison to score estimation. Score-based approaches to diffusion extend to discrete states, although they typically further build upon advanced continuous time Markov chain theory. In particular, SED derives and optimizes an evidence lower bound that is a function of the score model, obtaining state-of-the-art log likelihoods among diffusion models. We use a much simpler approach that requires no advanced theory. Comparison to BERT. Our work provides a principled way of making BERT generative when trained with randomized masking rates. Previous work on generating from BERT used Gibbs sampling or ad hoc methods. The connection between BERT and diffusion was first made by Austin et al. Their objective effectively involves unmasking. He et al. Additionally start training from a pre-trained BERT. However, both works use an objective that is less numerically stable than our objective. Austin et al. Describe in their appendix how their evidence lower bound can simplify to a weighted masking loss similar to our simplified diffusion loss, but using a more complex formula for the weights. However, they do not train with that objective. Our work derives a simpler expression for the average of masking losses, implements it, and obtains better likelihoods. Conclusion. In this work we explore mask diffusion. With a well-engineered implementation that supports a simple variational objective, we attain state-of-the-art diffusion perplexities on language benchmarks and demonstrate how to efficiently convert BERT-style encoders into generative models. Given we are working on language modeling, we carry any of the inherent risks and opportunities that come with this line of research,